Today we're going to look at radicals and roots and how to simplify them. So most of this should be review material. So an example of this would be if I did the square root of x. So the square root of x, you know that there's no number here. And if there's no number here, it's just assumed that it's a 2. So this is the second root of x. So another way to write that would be x to the 1/2 power. Okay, you're just making a fraction, and the denominator is always whatever number is outside of the radical. Later, we are going to do more complex examples where we have numbers inside the radical, but for today, these are just numbers outside of the radical. So if I had written something as the 5th root of y, that is the same thing as y to the 1/5 power. So if we look at your homework examples and we look at problem number 1, the problem is written as p to the 1/5 power. So that means that is the 5th root of p. Okay, we're not solving these, we're not trying to find an answer. The only thing we're trying to do is to be able to go back and forth between these two forms. This right here is called exponential form. And on this side, this is what's called radical form. So if we look at example 3, you have 6n to the 1/2 power. So that's the same thing as the square root of 6n. Because they're in parentheses, that 1/2 power applies to both things. So in problem number 5, where you are asked to do the 3rd root of 7v, okay, we could not write that as 7v to the 1/3 power without putting parentheses around the 7v. That 1/3 has to apply to both the 7 and the v. And in problem number 7, we're doing the 6th root of b. So that is the same thing as b to the 1/6 power. So that's the difference between writing things in exponential form and radical form. The other things that we have to do with radicals is to be able to simplify them. So if we look at problem number 9, the question that you're asked to simplify is the square root of 44. So what you want to do here is think about what is the largest perfect square that goes into 44. Because 1 goes into 44, the next perfect square is 4. 4 goes into 44. 44 is 4 times 11. So all I've done here is written 44 as two separate things. What I want you to do is always circle what is the perfect square. So in this case, that is 4. That means we're going to be taking the square root of 4. So we're doing the square root of 4 times the square root of 11. So the square root of 4 is 2. The square root of 11 cannot be simplified any further. So our final answer here is 2 times the square root of 11. That's how we would simplify the square root of 44. Alright, in problem number 11, we have the square root of 48. 4 also goes into 48, but you always want to pick the largest square root that goes into this number. So always start with something close to half of what the number is, and then kind of work your way down with perfect squares. So 48 is 16 times 3. So our perfect square here is 16. So that's what we're going to be taking outside and taking the square root of. I'm not going to write this intermediate step here. I know that I'm doing the square root of 16, which is 4. I'm taking that one outside. But 3 is not a perfect square. I didn't circle it, so that means I'm leaving it inside. So the square root of 48 simplified is 4 times the square root of 3. We can also look at something like problem number 13, where it's -5 times the square root of 147. So 147 Okay, you want to think of some really big square roots here. This is a guess and check thing where you're trying to figure out what goes into 147. Okay, that -5 has to be part of my answer. It has to stay there the whole time. 147 is divisible by 49. That's the largest square root. So that's 49 times 3 is what gives us the 147. So my perfect square here is 49. That's what I'm going to be taking the square root of. The square root of 49 is 7. So that's what's going to get pulled to the outside. And this is a multiplication problem. It's -5 times the square root of 147. So when I take the square root of 49, that's 7. That's going to get multiplied by my -5 that's already on the outside. -5 times 7 with the square root of 3. So my final answer here would be -35 times the square root of 3. We can also add and subtract our radicals. If we look at problem 15, it's -3 times the square root of 2 plus 3 times the square root of 2. Okay, the whole idea here is that you have to have like radicals in order to be able to add or subtract them. So in this case, they are both square roots of 2. So you're just doing your mathematical operation with the number on the outside. This is the same thing as saying -3x plus 3x. Okay, but instead of x, our variable is the square root of 2, or our like term is the square root of 2. So -3 square roots of 2 plus 3 square roots of 2 is going to give us 0 square roots of 2, which we would just write as 0, because 0 times anything is 0. In problem number 17, where it's 3 times the square root of 6 minus the square root of 6. Okay, so we have 3 square roots of 6, and we're taking away 1 square root of 6. That's going to leave us with 2 square roots of 6. In problem number 19, we have 3 square roots of 5, and we're going to add 2 square roots of 5. So that means we're left with 5 square roots of 5. Again, notice in these problems, the radicals, what's under the radicand, that number is the same. Okay, in problem number 21, -3 square root of 20 minus 2 square root of 20 is going to leave us with -5 square root of 20. Now you should be saying to yourself, can the square root of 20 be simplified? You could either simplify it here before you subtracted, or you can simplify it here. Well, I know that 20, I'm going to write this down here. 20 is the same thing as 4 times 5. And 4 is a perfect square. So that means I can pull that perfect square outside. I can take the square root of 4. The square root of 4 is 2. So I'm going to take -5 and I'm going to multiply it by 2, and then I have the square root of 5. So my final answer here is -10 times the square root of 5. Now you can always check these by starting off with your original problem, getting it as a decimal, making sure that it equals the same thing here. Alright, the last problem I'm going to walk you through is problem number 23. Okay, it's the opposite of the square root of 3, or -1 times the square root of 3 minus 3 times the square root of 12. We cannot do this operation without having like numbers under the radical. This one is simplified as far as it can go, but this one is not. The square root of 12 has a perfect square as a factor, and that number is 4. 12 is the same thing as 4 times 3. 4 is a perfect square. So I can take that to the outside. The square root of 4 is 2, so I'm multiplying that by the outside and having 3. So I have negative 1 times the square root of 3 minus 6 times the square root of 3. So my final answer here is negative 7 times the square root of 3. Alright, so the big key ideas here are being able to rewrite expressions either in radical form and exponential form, depending on what you've been given. Okay, that is numbers 2 through 8. And then in 10 through 24, you are simplifying your expressions, whether it's one radical or it's adding or subtracting those radicals. Okay, so go ahead and finish up the evens for your homework assignment for either Monday or Tuesday, depending on when I have you. If you have more questions on this, please come into Cav Morning on Monday or Tuesday.